in this homework, I will be deriving the thermodynamic factor from the equation for driving force. So in the equation for driving force, we have driving force is equal to the mole fraction of component I over RT times the gradient of the chemical potential of component I. So where the chemical potential is the Gibbs free energy per mole of component I, it's written as chemical potential equals chemical potential at standard temperature and pressure plus RT times natural log of gamma, or the activity coefficient of I, times the mole fraction of I, where the activity coefficient of I represents the non-idealities of component I. And this gradient here just represents that we're taking the partial derivatives of the chemical potential of component I and putting them into a vector. So gradient. So if we want to take this gradient and solve for the derivative of the chemical potential, we can think of the chemical potential as the change of the chemical potential with respect to position. So we can rewrite this as dI equals xi over RT times the change with respect to position of the chemical potential. And then we can plug in the equation for chemical potential. And when we take this derivative, the derivative of a constant is 0, so we can forget about this term. Once that term's canceled out, our constants will also cancel out. So we can rewrite as xi times derivative of the natural log of gamma I times xi, which we can then rewrite as the derivative of the natural log of xi plus the natural log of gamma I. We take these derivatives of xi times 1 over xi times change of the mole fraction of I with respect to position plus xi times 1 over gamma I times the change in the activity coefficient with respect to position. So then these terms will cancel out. We're left with change in mole fraction with respect to position plus xi times, and we can put this back into the form of natural log of gamma, so we'll have the derivative with respect to position of natural log of gamma I. But then we have to remember that the activity coefficient doesn't actually vary with position, it varies with composition. It is the composition that varies with position. So if we break this down farther, we'll then have mole fraction times derivative of gamma I with respect to the composition of some component J times the change component J with respect to position. So when we look at the terms in this equation, we can think of this term as being like the gradient of component J, so the change in the composition of the mixture with respect to position. And we can think of this term as accounting for the non-idealities in component I because of the activity coefficient. So then we can take this equation and write this for a multi-component mixture. So for example, we could write this for a 3-component mixture. So for the driving force of component 1, we would then take this equation and solve it out. So first, we have the change in component 1 with respect to position plus x1 times change the activity coefficient component 1 respect to dx1, oh my goodness, times the change in the mole fraction of component 1 with respect to position. And then we can write this out for mole fraction of component 1 times the change in activity coefficient component 1 with respect to component 2. So we change J to 2 times the change in the mole fraction of component 2 with respect to position plus mole fraction of component 1 times the change in natural log of activity coefficient of component 1 with respect to component 3, mole fraction of component 3 times the change in composition component 3 with respect to position. And then we can do this for all 3 of our driving forces in our 3-component mixture. So here we have our driving forces for our 3-component mixture. So as you can see, when we calculate our driving forces, we get a vector of values. And in order to get this vector of values, we can multiply by 2 other vectors. So if we have our driving force for component I, this vector right here we can think of as our mole fraction gradient. So the change in mole fraction of component J with respect to position. So for our 3 components, we'd have change in x1, respect to position, dx2, dx3. And this other matrix we can think of as being the thermodynamic factor. This term right here, which accounts for those non-idealities due to the activity coefficient. So if we plug this term into our matrix, okay, so once I've plugged in this value for my matrix, the matrix is almost complete. The last thing we have to add in is this Kronecker delta. And all the Kronecker delta does is that when I equals J, so that when the activity coefficient is referring to the same component as the mole fraction, so for example, the activity coefficient of component 1 and the mole fraction of component 1, the Kronecker delta will equal 1. When I is not equal to J, the Kronecker delta is equal to 0. So for example, when I equals 1 and J equals 1, we need to add the Kronecker delta. When I equals 2 and J equals 2, we need to add the Kronecker delta. And when I equals 3 and J equals 3, we need to add the Kronecker delta. So the last thing we can do is now pull this thermodynamic factor out of the matrix form. And we get that this thermodynamic factor equals this Kronecker delta term plus the term that we had up here with the activity coefficient. So the derivative of natural log of gamma I with respect to some component J at constant temperature and pressure. So I just finished filming this, and I don't want to do it again, but I did realize when I was writing out this thermodynamic factor part over here into my matrix, I forgot to multiply by xi for each of these terms, and then obviously xi down here, so just need to add that in.